Hello, this is going to be a quick tutorial on how to use srlife. So srlife is a solar receiver Python package that can determine not only the temperature distribution within solar receiver tubes of various materials and with various heat transfer fluids, but it can also do a structural analysis considering the full plastic deformation of the tube, as well as things like creep and stress relaxation. And then it can perform a lifetime analysis on it, considering the creep rupture time and the number of fatigue cycles, and using the creep fatigue interaction diagram to properly determine the number of cycles that a given tube can undergo. And this can be tubes for parabolic trough receivers or for central receivers, so solar power towers. But really it can just be used on any type of tube with heat transfer fluid and thermal boundary conditions, and we'll get into that in a bit. So srlife is a Linux package, and as you can see, I'm on Windows. So what I'm going to do is I'm going to go into my VPN. Okay, so now I'm on my other screen because I guess my school's VPN doesn't allow me to open it up on a separate screen. So type in Global Protect on my Windows start menu, and I've already kind of filled in a lot of the login credentials, so I'm going to use the full VPN. I'm connected to the school's Wi-Fi. I'll hit connect. Okay. I have to input my login credentials. Okay, now I'm connected onto my school's network. What I can now do is I can remote into a Linux machine using the remote desktop connection app. So this is the computer that I'll be remoting into. I've already filled in my login credentials and everything. You might have to like sign in and things of that nature. But for me, I can just log in easily. Alright, so now I'm on the Linux computer. As you can see, I already have a lot of stuff open. I just clicked on this top left corner over here to get all my apps in one window. But I think what I'll do is I'll go into a new workspace. And so everything's all clean. And what I'll do is I will go and go on to Firefox. Okay, so I pulled up a few windows. One is the srlife documentation, which I'll provide a link in the description, but it's pretty in-depth and goes over how to install, run, and explains the different modules that srlife has in its official release, its latest official release. So another website you want to also check out is the srlife GitHub. Now, as you can see, the last official release for srlife was on October 13th of 2021, but the last GitHub push to this latest developed version was in late June. So this is a more developed version, a more, I guess, experimental, but has all the latest features. And I'll show you how to install both. And then this paper, Design Guidance for High Temperature Concentrating Solar Power Components. Now there is no published paper describing how srlife works. You can possibly email Mark Messner for that. But this report goes into fairly detailed description of kind of like how srlife kind of works under the hood, or at least the general equations that it uses. So for example, for the creep analysis, determining the time to rupture, it uses this Larson-Miller correlation. At least I think it uses that in the latest version. I have to double check. But this is a generally pretty good description of how everything works, and includes, you know, where it's pulling the numbers from for different materials like 740H or Haynes 230. And these are the different materials of the receiver tubes, I should clarify. And what's also nice is it comes with some sample problems, so you could essentially read the problem and you know, do the math yourself just to make sure everything's making sense. Now the sample problems aren't included in the example problems with srlife, so I went ahead and recreated sample problem 1 in srlife to compare, but I'll get into that in maybe a future video. So for now, let's get into installing srlife. So what you're going to want to do is open up a new terminal window. So we're going to open a new terminal window. And as you could see, it says base environment over here. Now, if it doesn't say that for you, it probably means that you don't have miniconda installed. So essentially what we're going to do is we're going to install miniconda, which is a Python package manager, and Python, and just a general virtual environment manager that's very commonly used. So yeah, just to let you know, these are not my suggestions. It's Firefox likes to not be very targeted with the advertisements, but essentially what you want to know is you want to download miniconda so that you can so that when you download srlife, none of the packages associated with srlife and subsequent packages you download interfere with any other projects you're working on. So generally, each time you make a new project, you want to create a new virtual environment. So if you don't have miniconda, you just go over here and basically you just download whatever version. If considering we're on Ubuntu, you would download the latest Debian release. So I got downloaded this one. Then once you've downloaded it, what you would do is you would change directories CD into your downloads folder, and then you would basically what's verify installer hashes? Let me just check this out for a second. Oh, okay. So you would enter SHA 256, and then so what I did was I typed in this line into my terminal, and then I pressed space, and then I typed the first letter of the file, or the first few letters, and then I pressed tab to autocomplete. So you'd press enter on that. I already did this, so I'm not gonna repeat this. And then you would just run the bash script. I'm not too familiar with Linux, so maybe I might not be getting all the terminology right. Then you enter that, and then you should have Anaconda, or miniconda installed. Anaconda is just miniconda plus a bunch of other stuff pre-installed. So you should probably download this if you want it to be a little bit faster and less cluttered. So Now what we're going to do is we're going to look at the environments that we have. So I have a lot of environments, so I'm going to do conda environments list. So this gives me all of the environments that I created. And each virtual environment is like its own place where you can install Python and different packages, and they don't interfere with each other because everything is anyway, never mind. So yeah, they just don't interfere with each other. So as you can see, I have a bunch of different conda environments. I already have a conda environment called srlife, so I'm not going to create a new one. But for the sake of this tutorial, I'll do conda create new name srlife, and it has to be, it shouldn't have any spaces. It should just be, you know, like one word. It shouldn't have any like weird characters, just like any other, you know, file or directory name. So we call this srlife tutorial. Enter. And if you want to know where I'm getting like how I know how to use these commands, what you can just do is type in conda. Well, yes, conda managing environments. I'll put the link to that in the description. Oh, whoops, it took me into a different workspace. But essentially, this managing environments webpage, which I'll put in the description, is pretty detailed, and it goes into like how to use everything. So let me go back into my other workspace. Okay. Yes. So now we have an empty conda environment. So if we do conda activate srlife tutorial, we'll see that when we do conda list, this lists all the packages we have. We can see we have no packages, which is what we want. So if I am remembering correctly, srlife runs on Python 3.7 or above, but I don't think the latest versions are compatible with Python 3.10, so I'm going to install Python 3.9. So to do that, I'm going to do conda install Python equals 3.9. Now, I could specify a specific release doing this, or I can just say Python 3.9, and it will just give me the latest version of 3.9, because there's like sub-versions, I guess. So I'm going to do -y, which just means that you know, I don't have to click yes. So it's going to install that. And it's also going to install pip, which is the Python, which is like the default Python package manager. Now, generally, they say that you shouldn't, you know, mix pip with conda because they're two separate package managers, and sometimes there can be conflicts and it can be confusing, but if you're kind of smart about it, there shouldn't be that much of an issue. So we can, I guess we can go look at this overview of srlife, which basically says what I said before, where you know, it evaluates the lifetime of a receiver based on these thermomechanical boundary conditions. I think something that's important, so you should probably read this, but what is pretty important is the units used. You want to make sure you're using the right units, because a lot of problems I ran into were just like simple unit mistakes, like I was using pascals instead of the default megapascals. So this is just whenever you see a function that takes in like temperature or whatever, just remember these are the default units. And they might seem like odd, Like, why would you use, hours for time instead of seconds, or millimeters for length? And it's just because, creep rupture time is in hours, and a lot of things in srlife are on the order of millimeters, such as the tube thickness and things like that. So let's go into the installing srlife page, and yes, as you can see, it says these are the Python versions that it's compatible with. So we downloaded 3.9, which is good. So we're gonna install the latest stable release for srlife, doing pip install srlife, and as I said before, make sure your environment has been activated. So it should say it over here. I'm gonna click enter, and then it will install srlife for us. And that's basically how you download the latest stable version of srlife. Right. So that's one way of doing it. Another way of doing it is downloading it directly from the GitHub repository. So the latest experimental version. Now these instructions over here are kind of how you would do it outside of using, well, I just have a different version of doing it. So what I'll do is I'll deactivate my condo environment. So we just installed srlife, the latest stable version, and we'll get back to that in a bit. But what I'll do is I'll deactivate this environment, and then I'll create a new environment so I can download the latest experimental version, so that they're in two separate environments and they don't conflict with each other. So srlife tutorial experimental. Maybe you can name this something else, maybe something a little bit easier to remember. But now we'll just be doing that. Great. So we'll do pretty much the same thing. So actually, what I could have done is I could specify packages to download while I'm creating the environments. I could have done this, but just, I guess, to explain each step of the way so it's not confusing, I'll just continue to do this. So what I did was, the way I'm getting this now in terminal is I'm just using the up and down arrow keys to look at my previous commands, so I don't have to retype it in again. So I'm installing Python 3.9 again, as before. I also have, so this is on the GitHub repository. If you want to download it using Git, then you need Git on your computer. So I have Git, and I can see that by just typing in. So I get all these things. If you don't have Git, what you can do is you can install it. So git install Linux. Yeah, so if you need to install Git, then this is pretty much how you do it. You do need sudo user privilege. Basically means like you can like make modifications to the computer. It's like admin rights kind of. So I'll leave a link to this in the description if you don't have Git either. But assuming you do have Git, then what we'll do is we'll navigate over to the srlife GitHub repository, and we will go under this code tab and copy the URL. Alternatively, actually, if you don't want to use, if you don't have the super user abilities, what you could just do is you could download the repository manually and then extract the file. Now, this doesn't have a lot of the same advantages as Git. You can't really like pull new updates just using the command line and using other things like that. But if you don't have admin privileges or super user privileges, this might be the way to go. But we're going to do this from the command line just because we can pull new updates once they're released. So we're going to do git. Well, first we're going to change to a directory that we want srlife to be in. So I'm going to change to my documents directory. And what I'm going to do is I'm going to make a new folder called srlife tutorial. So this creates a new folder, and we could obviously go into the GUI and make a folder ourselves, file explorer. But I guess this is cd srlife tutorial. All right, so now we're in this new directory. So now what we're going to do is we're going to clone the repository, so git clone, and then paste that in. And now if we go into our file explorer, so what I did here is actually correct, but as you could see in the video, I'm not getting all the files, and the reason is because I had already previously cloned the repository. So the steps are correct, but what I'm going to do now is I'm going to fork the repository, and you should also do this if you want to make modifications to srlife, but cloning the repository should have worked previously. But now we'll go into forking the repository and installing srlife that way, in case you want to make any serious modifications. I think for most repositories you can just clone them, but I think that you can regulate the permissions on that. So what you should do is, if you want to work on the latest version of srlife and you want to make modifications and things like that to it, what you can do is you can fork the repository and create a fork. I don't know why it says I'm AIAA SBU. Oh, okay, because I have multiple accounts. So yeah, you can fork repository. As you can see, I've already done this. You can name it whatever you want, and then you can create your fork. Now, because I've already done that, I can go into my, well, let me just go into my repositories. So as you can see, I have my own forked version of srlife, and now I can go and clone that. Now you do need a GitHub account. Another thing you might notice is that you have to sign into a GitHub account. It's kind of annoying to do because you need you can't just put in, when it asks for your password in the terminal, you're going to have to go into, I believe it's settings, and then, yeah, you generate some kind of key for it somewhere over here. There's another link I can leave in the description if you've never used it before, but I'll go back here. So we're going to just do the same thing that we did before. We're going to clone this repository. And as you know, I haven't tried out this. I'm sure that this also works, and this installs the latest version of srlife. But what I want to do is I just want to have a version that I can also edit the source code of if I want to make changes to it as I see fit. So I'm going to do git clone again. paste. Alright, so I think I realized that my problem was that I have a cloned repository of srlife in another folder. So there's like some conflicts with that. Now I could create a new branch and all that stuff, but I think the simplest thing to show what I'm trying to accomplish is to just download the file directly from the website. And then show in folder, extract. Let's extract it to where we want it. Close. Okay. So now, yeah, I just manually downloaded it. There's just a problem with the way Git was tracking my files because I already cloned the repository. It should work for you if you just clone it from a fresh fork or whatever. But what I'm going to do is I'm going to cd into this folder. Okay, so you want to cd into the folder where it has the setup.py file. And then to install it as like a developer, so we're still in the srlife tutorial. EXP stands for, I don't know, something. I don't know my name to that. But to run it as like a developer, you do pip install -e dot, and then it looks for the setup.py file. So now basically srlife, these files should be, if we we should be able to just import all this stuff from any directory as long as we're in this conda environment. And if we modify these, it should modify everything else. Right. So what I'll do is I will go into VS Code. I will yeah, we can go into File Explorer, open folder, find the srlife folder we just opened, navigate to the examples, and then we have our setup file. So now we should be able to just run this. Using this. So you want to make sure that your proper conda environment is loaded. So the way you do that is you go into, you want to make sure that the proper version of Python is being loaded. So what you do is you go down over here, bottom right corner, you click on the environment that you want. So that'd be this one. And then let's rerun this. Okay, well, that worked. But I want to run this in the interactive window. Let's install this. Okay. I think if we want to interact with a lot of this stuff, we need to do conda install notebook. So let me just go do that. This is just downloading all the Jupyter Notebook stuff that I can integrate with VS Code. Alright, so if I want an interactive window with this, I just do pip install ipykernel. Let's close this in the proper environment. Alright, it ran. So as you can see in the variable section, we can just go through this code, explain what it does. So yeah, let's step back here. So we installed srlife via pip, which is the latest stable release, and we installed it from the GitHub repository either by downloading it or by using git to clone the repository. Now I'm currently in the latest version using the cloned repository, and in the cloned repository I navigated to the examples folder, which has the tutorial file in it. So the tutorial file, as you can see, cloned from srlife, has a setup problem Python file and a run problem Python file. Now, essentially, the setup file defines the tube receiver geometries, thermal boundary conditions, and the mechanical boundary conditions over a given cycle. So a cycle is typically defined as like 1 day of operation. So startup to shut down. So like, sunrise to sunset basically. And something to note is that you're able to define the mechanical boundary conditions, or you're able to kind of modify the mechanical boundary conditions between tubes. So once you kind of define the radius of the tubes and the thickness of the tubes and the material of the tubes, or rather not the material, just the geometry, you can specify material once you actually run the problem. Once you specify the geometry, you can specify whether or not the tubes are kind of disconnected from each other, or if they're rigidly connected, or if they are connected by some kind of spring, and you can define the spring constant. Now, generally speaking, srlife is able to use the, I think it's the multi-process library, so it's able to run individual tubes on individual cores or threads of your computer. So if you specify rigid or a spring constant for the way that the tubes are connected together, you won't be able to run it as fast. So I generally, whenever I specify the tubes, I specify them as disconnected for analysis. So we'll get into that later. This is basically just like defining an average day. So it talks about boundary conditions. You need to specify a temperature and boundary condition, pressure boundary condition for the fluid inside of the tube. And, well, yeah, you need to specify two thermal boundary conditions, one on the inside, one on the outside of the tube. So this is just basically going over creating that. So in this tutorial file, he creates a flux function, which can specify the flux on the tube, on the outside of the tube, in units of, I guess it's watts per millimeter squared, but if you go back, yeah, so watts, somewhere over here. Yeah, flux is in watts per millimeter squared. Let's go back. So you specify the flux on the outside of the tube. What he also does is he specifies the fluid temperature on the inside of the tube as a function of height in the tube. You know, srlife just takes discretized points, so you don't have to specify these functions. This is just to make things simple. If you have actual data to take in at the boundaries, then that's the way you would do it. So then, yeah, it just gets into like how to do that. So I'll run through that in the code. So, one thing you can do in Jupyter Notebook, or not Jupyter Notebook, one thing you do in VS Code is you can kind of create these individual cells. So, if you do, and this is only if you have the IPy kernel interactive stuff installed. If you do hashtag 2% symbols, you can divide each piece of a script into cells and run them like a Jupyter Notebook file. So if I run this cell, alright, so this is a cell. This basically imports srlife, so we know, and imports numpy, which is, you know, using for numbers and all that stuff, or for arrays. So importing that's fine. This just helps with like debugging and kind of explaining what's going on. So first couple lines specify the period, which is the number of hours that a cycle occurs. So this is specifying 1 day, so you specify a period of 24 hours. You could do 1 day and specify less hours, so like 16, and then you'd use something called a cycle reset heuristic. This, as I mentioned before, is specifying how the individual panels in a receiver are connected together, like how the individual tubes are. So specifying disconnect means you can solve them in parallel. Then, so model is basically the receiver object. So you specify it by period in hours, the number of days, panel stiffness. Tube stiffness, we're going to change this to, I always change it to disconnect just because usually I'm running multiple tubes at once, and I would like them to be solved in parallel. So this creates two panels. Each panel has, oh, interesting. I think this is supposed to be, okay, yeah, each panel has this tube stiffness parameter in it, which specifies the stiffness of the tubes in the panel. This specifies the receiver geometry, and then this is how many nodes are in the radial direction, the circumferential direction, and the height of the receiver. Generally, the 2D heuristic, so basically approximating the tube temperature distribution as only being important in the circumferential and radial direction, and kind of ignoring the temperature and stress in the temperature in the z direction, the temperature gradient. Sorry. That's a pretty good approximation to make. So generally, it doesn't really matter how many of these you specify if you're going to just use the 2D heuristic anyway. And then these are all functions for specifying the flux and things like that, and we can get into that later. And these are just more functions for that. Function specifying fluid temperature, pressure. This is pretty important. So this specifies basically how many time increments you're going to go throughout the day. So it has to start at 0 and it has to end at basically the number that you specified in your period. So it has to equal this number. And this function just creates a series of numbers from 0 to 24 with a total of 49 numbers in that array. But what you could do is you could space out the values in your array during in like more of a smart way. So you might say like you know, during the middle of the day, temperature doesn't change that much, so you can just put all the time nodes near startup or shutdown. But for simplicity, you could just have a uniform distribution of time nodes. So then these functions, they basically turn so then these functions are basically what you would pass in, these arrays are what you would pass into the tube objects for the fluid temperature and for the flux. So to kind of illustrate that, we can open up the arrays. Let's open up the, I guess, the time array. So this is for the fluid index. Oh, I'll have to install pandas. Okay, let's go do that. So yeah, we'll install pandas so we can actually see what the arrays look like. So let's go over here, open up this time one again. And as you could just see from the shape of it, that the first dimension is the number of time nodes, and the second dimension is the number of z nodes, the axial nodes. So if you were to recreate, if you were to, not use these functions but just pass in your own data, you just need to know that this is going to be the shape of this like time h mesh. And then back over here. Same thing with the ZH. So just oh, never mind. Let's ignore that. So yeah, the exact shape of these, this is just kind of for discretizing the functions that were specified previously. I think what matters most is this part of the code, the actual setting up of each of the tubes, and we can kind of break that down. So to specify a tube, you want to give it the dimension, so radius, outer radius, thickness, height, and the nodes, and you also should give it a initial temperature distribution. So right here, it specifies that the initial temperature of the entire tube is equal to the base temperature, which was just the ambient temperature that was specified somewhere else. So T base is I guess pretty high. Huh. Yes, this is an interesting. I typically set it to the ambient temperature, but I guess in this example file, it doesn't really, this tutorial doesn't really matter, but usually I set this to like ambient temperature. You give it a set of times, so the times are just that array from 0 to the end of the period. And you could, and then you need to give it two thermal boundary conditions. So this specifies, this set BC method specifies a convective boundary condition, and this last string here says to put it on the inside of the tube. You also want to give it a location, so because it's on the inside of the tube, you're going to go from the outer radius minus the thickness of the tube. And then you give it tube height, things like that, times vector again. Then you give it a basically an array. So what we should do is we should go over here and actually visualize that array. So the array that we need to give this convective boundary boundary. Oops, I messed that up. Can I rerun this? Oops. Okay. Fluid. So as you can see, the fluid temperature array is just going to be how the fluid temperature varies And the first dimension is with time, and then the second dimension is each c coordinate. So you pass that here. And you might want to think about how you would create that array. And then we can see that this is a multi-dimensional array of dimensions time, theta nodes, z nodes. And then this is just a one-dimensional array of dimension time. So the pressure varies how it varies with time. And then that's basically how you set up a tube, and then you add the tube to a given panel, and you can give the tube a name to refer to it later on. And then you add the panel to the model, and you give the panel a name as well. And then you save that and save it as a specific file. So once we've, run our script, we'll generate an HDF5 file, which is basically just a storage file that has, it's kind of like a JSON file where you can specify like a hierarchy, like an index, like a format for a file structure. So you run, this is the setup of the problem, the geometric and thermal and mechanical setup. This runs the model in actually in srlife. And Alright, so once you set up your file and you produced your HDF5 file for your receiver model, then you can go into the run problem part of the tutorial. And here's when srlife actually executes and runs everything. So you load up your file, you then specify what type of fluid, heat transfer fluid you're using. In this case, it's just regular chloride salt. As you can see here, it says base. So to illustrate what that means, we can go into the srlife data fluid, and then open up the salt file. Now each material has an XML file in the following format. I believe that this is to be compatible with NEML, which is a materials, I'm probably butchering what it actually is, but it is some kind of like structural material solver written in C++. So this is kind of in a format compatible with that, or analogous to that. But anyway, specifying base basically just means that it's this, it's using these values. I think other files have more complicated structures, so this is, oops, let's see. This is the deformation. Right, so as you can see, when we go into the deformation, so the structural file for 740H, you can see that there is a base model with base values, and there's also an elastic model, so it uses, does the elastic stress versus the whole plastic and all that stuff. But, back to running the actual problem though. So you specify base, then you specify a thermal, deformation, damaged material. So you specify that we're going to use 316H, that they're all going to be in its base format. Then what you could do is you can add a heuristic. So by default, srlife runs a full 3D FEA and thermal analysis and all that stuff. And that can be very computationally expensive. So what this is doing is it's using a heuristic on srlife to approximate the tube as just 1D radial heat transfer. You could, and so to specify that, you need to specify the height of the tube to do it at, and the circumferential position. So this is at the crown of the tube, or the zero position of the tube that's has the highest flux, if you specified the flux appropriately. But generally speaking, the 2D approximation, or the 1D approximation, isn't very accurate, so we're going to do 2D. And as a result, you only need to specify the height. This basically is just a bunch of parameters. You might want to change these if stuff isn't converging. But generally speaking, all these things are good. So, yeah, as I've said before, you want to run multiple threads if you have multiple tubes, panels, because it's faster. Generally, this is the advice that I got from my advisor, to run with one less core than the amount of cores that are available on your computer. So if you have 4 cores, run with 3. So on this computer, we can run as many cores as we want, because I believe there's around 20. So yeah, you can specify what different solvers to use. We'll get into that, the details of that much, maybe for a future video. And then you can, basically this sets up all the different solvers to use, and then to actually solve for the life of the receiver, you do this solve life function. And then this just saves the data to a VTK file, which can be viewed in pair view, which we can do. But let's just run the file and see what happens. So as you can see, the thermal analysis was done in about a second, but the structural analysis is going to take a lot longer. Now, I think it might be taking longer. As you can see, so there's 4 tubes, but it's only showing 2 tubes. So I think I might have messed up somewhere in my file specifying what was connected and what was disconnected. Or not, maybe I'm wrong. I guess we'll just run the file and see what happens. But I might want to generate another one of these and just call it model 2 and see what happens if I run it again. But because it's doing the full plastic strain, creep strain, all that stuff. Stress relaxation, I believe, might be included in this. Then, unfortunately, it's going to take a long time to actually run. So as you can see, yeah, there was a problem before where I guess I had connected 2 panels or 2 tubes by accident, but that fixed it. Time difference wasn't significantly different. It was only about 15 seconds saved, so It might be something to look into. But another thing that's interesting is the life is extremely low, and I think that might be a result of the fact that our material is stainless steel right over here, and also from before where the base temperature is set to be like 800 Kelvin or something like that, 870 Kelvin. I don't know, I can't do math. 820, okay. But that's basically how you set up problems in srlife. A couple things. So the life should be around 10,000 cycles. I think that corresponds to about 30 years, if I remember correctly. So yeah, about 30 years is what you want to shoot for. So otherwise, the documentation is pretty good. Just some things to note. So you can add a heuristic. One heuristic that is commonly added is the let me scroll down for a little bit. Cycle reset heuristic. So what you could do is, instead of specifying the full 24 hours, what you can do is go up to like, I don't know, how long does this tutorial file last? Scroll up back over here. What you could do is you could say, okay, well, after hour 12, there's like no real activity going on. So what you could do is you could go to this cycle reset heuristic, and you could say, just copy paste this. You can add it for each part of the tube. So you would do that in the run problem. This would probably go over here. You would do, I believe, solver dot add heuristic. Cycle reset heuristic. This might be done already in this problem. Check to look at it. They might do it here. Oh, yeah, here we go. So let me just copy and paste that. Put it over here. So I forgot the managers. And that's in the right location. So as a result, then we can shorten down the period to 12. 12. And that allows us to save on some, basically cut the problem in half, which is pretty nice. So this would be period. Right. And if everything goes smoothly, I think we should be able to run it, let's call this model 3, run it in the same amount of time. So let's generate this file so that That's fine. So, problem is that this is a float, and now down here, it's not a float. It's supposed to be an integer. So let's convert that to an integer. And then, I'm surprised I didn't catch this. Maybe it did and I just didn't notice. Note that I made the last bound an integer as well. You only need to make the number of nodes an integer. What is going on? Oh, I'm in the wrong, I was in the wrong window. I think. Right? Yep. Okay. Oh, silly me. I guess I'll run it again. Oh, it's already here. Okay, well, that must have been frustrating for anyone who was watching. Let's run it again, and we're good. Okay. So, now we'll run model 3. Well, do I have to make... I guess I didn't have to change anything, because I didn't change anything in this file. Oh, no, I did. Okay. I think I'm going insane. All right, let's save this, and let's run this in this window. And we can make a comparison. Just make sure we have everything right, and I'm not going crazy. And we will run this. It should take. Oh, I'm silly because I didn't. Okay, yeah. Let me stop this. I am quite silly because I forgot that I didn't cut the nodes in half. I should do that though. I should do that. And that is my new problem. And now this should give me the same results. So if I run this in an interactive window, it should give me the same results as before. So, because if we look in our Jupyter variables, the times, basically same as before, but just goes up to 12. This should work. So, as you can see, it pretty much displays the same life as the previous runs. So, fortunately, it doesn't cut the time in half. It only saves about a minute or so, but that's still something. One last thing that I'll talk about is the actual fluid file. So, as you can see, this salt file just has temperature values and these other values. Now, these values are actually the heat transfer coefficient, and unfortunately, srlife, at least in this version, I think there might have been updates, but yeah, in this version, regardless of the flow rate, it just gives you like a constant heat transfer coefficient, which isn't exactly very accurate. So what you're probably going to want to do is, in the setup of the problem, instead of giving it an inner and outer boundary conditions where the inner one is the fluid temperature or the convective boundary, and the outer one is the heat flux. What you probably want to do is solve for the inner and outer temperature boundary conditions using your own thermal solver, and then have this be an inner temperature boundary condition, and you can find that over, I think over here. This kind of goes into the how everything's defined, and you know, the dimensions of like the nodes and things like that. So as I said before, time is always the first dimension, and then so on and so forth. But in terms of the two boundary conditions, you find that over here, and you would want to set a fixed temp boundary condition. So you would run an external thermal solver to get the inner and outer temperatures of the surfaces of the tube, the inner surface and the outer surface, and then you would basically make that your two thermal boundary conditions, and then you'd probably, you know, have lead pressure the same. And then that's generally how you use srlife. If there's any questions, you can leave them in the comments. I'll probably make another video going more in depth or kind of more organized, but this is just a general summary of like how I use the software. I don't have any involvement with the development of the software, so this is just like a simple how-to video. Alright, thank you.